When we start sampling, of course, what we would like to know is how big of a sample do we have to take in order to get a certain level of confidence. So we're going to get that level, we're going to get that sample size using the maximum error of the estimate. So here's the formula for the maximum error of the estimate. And you can see that there is an n here. That n is the sample size. So if we know what error we're willing to make, so that's what we might do right up front, is how much error are we willing to make? And at what confidence level do we want? Then we'll know sigma, and we can solve for n. So we're going to solve this for n, a little bit of algebra. So the first thing I'm going to do is I'm going to multiply by square root of n. Right, get rid of those fractions. So if I do that, it'll look like this. E times square root of n, that's equal to z sub c times sigma over square root of n times square root of n. Square roots of n on the right side cancel, and we get e times the square root of n is equal to z sub confidence level and times sigma. Now, let's divide by e. I'm trying to isolate that in. So if I divide by e, I'm just going to go ahead and do it. I get this. I'll do it up at the top here. I get the square root of n is equal to z sub c times sigma all over e. And now square both sides. If I square both sides, it'll look like this. Square the square root of n, okay, and then we get z sub c, the critical value, times sigma all over e squared. All right, so here's what we get. We get n is equal to, I'm going to write it in a bracket here, z sub c times sigma all over the maximum error of the estimate. And this gets squared. So there is our formula for finding the sample size necessary to get a certain level of confidence with a certain maximum error. And let's make an important note here. Because this is a sample size, it has to be an integer. So what we always do is round up. It's not normal rounding. You're always going to round up. Let's do an example. This is number 16 out of the textbook. And we'll do the whole thing here. Well, we'll do part A and D. So what's happening here is this. Overproduction of uric acid in the body can be an indication of cell breakdown. This may be an advanced indication of illness such as gout, leukemia, or lymphoma. Now, over a period of months, an adult male patient has taken 8 blood tests for uric acid. All right, so I've got N equals 8. What do we know? The mean was, out of these 8 tests, was 5.35 milligrams per deciliter. And the distribution of uric acid in healthy males is assumed to be this number right here. So I just summarized all that. N is 8, X bar 5.35, sigma 1.85. And what they want us to do is construct a 95% confidence interval for this true mean uric acid level. Let's start by writing our formula. X bar plus or minus E. Well, E we know is this. So it's X bar plus or minus. Now E is the z-score, as our critical value that is determined by our confidence level, times sigma over square root of n. All right, now they are asking for the margin of error. So I'm going to do this in 2 pieces. I'll do this and then this. Otherwise, I just do the whole thing directly on my calculator. But this is going to be X bar, which we're given to be 5.35, plus or minus. Now, this is our critical value, and we're at 95%. The critical value at 95%, you may remember, is 1.96 times sigma. Now, sigma is given as 1.85 over the square root of n, square root of the sample size, square root of 8. Now, computing 5.35 plus or minus, okay, 1.96 times 1.85 divided by the square root of 8. I got this. I'm going to round this to 2 decimal places, 1.28. All right, so there's our margin of error right there. All right, that's the margin of error. So they're asking for that. So the margin of error, 1.28. Now, if we make the subtraction and addition, we'll get 5.35 minus 1.28. That's going to be less than the true mean, which is less than, make the addition, 5.35 plus 1.28. And so I get this. I get 4.07 less than the true mean, less than 6.63. Now let's interpret this. So I'm going to interpret it like this. I'm going to say there is a 95% chance, because we did this at, 95 as our confidence level. So there's a 95% chance that this interval right here covers the true mean uric acid level in this patient. I'll draw a picture. So this patient does have some mean. We just don't know what it is. We constructed an interval, and we're 95% sure that our interval actually covers that true mean. So from 4.07 to 6.63. We're 95% sure that our interval covers that true mean. Now, there's a 5% chance that we missed it. So maybe, our interval is like this. It's just big because we got, say, bigger than usual samples, but we don't know it. All right, we don't know that that's what we have. We just are 95 times out of 100, we're going to get a good one. So now in part D, we're asked to decrease the maximum error that we're making. When we did this problem, we computed the maximum error to be 1.28. Now what we want to do is decrease the error and find out what size sample we need to get that. So here's the sample size formula. You can see that the error is in the denominator, and when you make a denominator smaller, which we are, right, we're going from 1.28 down to 1.10, when you make the denominator of a fraction smaller, the whole fraction gets bigger. So we're making this smaller, so the fraction will get bigger, which is the sample size. So if we decrease the error, we'll have to increase the sample size. So let's substitute our numbers and compute. We'll get n is equal to, now don't forget to square this, z sub c, our critical value. We're at 95%, so that's at 1.96 times, now this sigma was given, 1.85, but now divided by our new error, 1.10, and then we have to square all this. Now I'm going to do it in two parts. I'll get this number here, and then I will square it. Now when I did that, I got 3.296 ... I'm going to square that, so I'll just do that directly on my calculator. I'll square it. So when I square that, I got n equal to 10.866 ... Okay, now, remember, this is a sample size. It's got to be an integer, and what we always do is round up. So round up. So I'm going to make the sample of size 11. So at 1.28, at that 1.28, we got a sample of size 8 and got that error. Now we're going to decrease the error, and we need to increase our sample. Now I just want to make an arithmetic comment here. What we did here is we rounded up, right, from 10.866, we rounded up to 11. Now, this formula here for the sample size came from this formula. You may remember when we derived it. All right, now what happens here? In this formula here, if I increase the sample size, right, increase it from what? 10.866, make it a little bit bigger to 11. But nonetheless, I'm increasing it. Now, that square root of n is on the bottom. As I make the bottom of a fraction bigger, the whole fraction gets smaller. But the whole fraction is what? That's the error. So what we're actually doing now is we're getting even a smaller error than we have projected, right? We got this sample size of 11 we got that 11 trying to get an error of 1.10, but we increased the sample size, so we're getting an error even better, less than 1.10.